All about last time we were talking about this theorem. So given any ergodic invariant measure for the projective cocycle has associated to it some Lyapunov exponents, and the connection between the two is given by this. That the integral of function phi, this function phi is phi and the integral of this function with respect to the measure m is precisely the Lyapunov exponent, and moreover, the measure also sees the oscillated subspace Vj in this sense. That it gives full weight to the graph of this subspace. And then conversely, for any j, there exists some invariant measure m such that this property holds. In a sense, the converse is perhaps a little bit more interesting, because it says that all Lyapunov exponents can be realized through some invariant measure, realized in the sense of these two relations. The measure allows one to calculate the exponents, and in a sense it also allows us to calculate the oscillated subspace. So we had proven this already. The first part was done, and we were proving the converse. And what we have done so far is was to show that we already know that we already know how to construct this invariant measure here. Given any probability measure m0 and m we have seen that given any probability measure m0 in the product, any accumulation point M of the sequence 1 over n is PF invariance. Okay, so we already know how to construct invariant measures. Now we want to make sure that we are able to construct them in such a way that the properties there are true. Okay. Yeah. So for this, I'm going to look. Essentially, what I want to do is I want to choose M0 satisfying this property, not necessarily invariance. I will find some measure that has this property. I want to apply that construction to that M0. And I want to argue that the limit, the accumulation point, also has the same property. Okay. It's not difficult to see that if M0 has this property here, then the iterates also have this property because this subspace is invariant. The tricky part is to go to the limit. So in order to go to the limit, I need the following lemma. The set of probability measures M0 such that M0 of xv is 1. So the set of measures that give all the way to the graph of Vj is PF invariant and closed. That's my claim. Now, if I prove this, so if we take M0 with this property, such that M0 is 1, then all these iterates here will have the same property because of invariance. So the average will have this property. That's obvious. And then, since the set is closed, I can go to the limit, and then M of this set is also 1. Right? Now, one question that you may ask is whether this set is empty. Is there any measure that gives full weight to the graph of V? For instance, if you want to construct such a measure, well, the answer is it's not empty. And that's why I gave you an example before starting the proof, because the example answers this question. For instance, we may take sigma from M to RD measurable such that sigma of x is in Vxj for all j, for all x. This exists because the subbundle is measurable, and so it admits some measurable section. This is a sigma is a measurable section. Is a measurable section of Vxj. So first you take sigma in this way, and then define m0. You remember that any of these measures that project down to mu, I observed that they can be obtained by Rochlin as mu times this integration. So I'm just going to define m0 in that way, so that m0 is of E is the integral of delta sigma of x. Oof, this is so I wanted this integration to be given by this delta sigma of x. For each point x, I want to consider on projective space the delta mass. So how should I say it? Given a set E here, how am I going to measure the set? Well, one way I can define it is mu of the set of x in M such that x sigma of x is in E. It's the shortest, quickest way to define M0. Okay, so for each point x, I ask, is this point, this place where I want to put the Dirac mass, is it inside E? If so, I count the point x. If not, I don't count the point x. Okay, I can write this in a more complicated way, but it's equivalent. Integral of delta sigma x of E intersected with a vertical okay, this is 0 or 1 depending on whether this pair is in E or not, and then I integrate with respect to x. Just another way of saying it. Okay, so measures like this exist. And this lemma tells me that if I have any of these, the accumulation point also satisfies that property. So I'm going to check that the lemma is true. Proof of the lemma. So here's the picture. This is M. This is projective space, or RD. And here I have Vxj. For each point x, I associate the xj. So essentially, I'm again going to play. I'm again going to pretend that this subbundle is continuous. It is not continuous. It is measurable, but we know that measurable functions are continuous on 99% of the space. So that's what I'm going to do. Given epsilon, take k contained in M such that the complement of K has small measure and X goes to Vj of X is continuous on K, restricted to K. Okay. Remember that to say that a bundle is measurable is to say that it admits a measurable basis. So we just take a compact set where all the vector spaces that form the basis are continuous. So we have here a Cantor set, a compact set K with very large measure and restricted to this compact set the subbundle is continuous. So the set of pairs X, V such that X is in K and V is in Vxj. This is the graph of K, of the subbundle restricted to this compact set is a compact subset of M cross PRD. Right? The domain is compact and the function is continuous. So this is compact. And so I'm proving, I didn't say it, I'm first proving that the set is closed, and then I will argue that it's invariant. Okay, so take sequence Mn. Well, I have to find a name for this set. The set of S of mu of probability measures that project down to mu and satisfy this property is PF invariant and closed. So take Mn in S of mu, Mn converging to M0. The topology here is the weak star topology. It's always the weak star topology. So this S of mu is a subset of the set of measures that project down to mu. It's precisely the subset of those measures that satisfy this. Okay, so I want to prove that it is closed. I take a sequence in this set converging to some limit, and I want to prove that the limit is also there. Okay. Now, since that thing there is compact, we have that if I look at the measures of that set, I look at those measures and I want to compare with the measure of the limits. This in general is a tricky thing to do, but for closed subsets, there is something that we can say. And what we can say is that for closed subsets, the lim I always have to think for a closed subset, this is bigger. The lim sup, when n goes to infinity, of Mn of a closed set is less or equal than the measure of the set for the limit. Okay, this is just because this set is closed. Because this this set is closed. Okay. However, those measures Mn give full weight to the graph, right? Those measures Mn give full weight to the graph. So if I didn't have this here, if I erase this, then the measure is equal to 1 because they belong to this set, right? But I'm excluding something. I'm excluding the parts of the graph that are here. Okay? So that is, I have to subtract something. Right? I have to subtract the weight of the parts of the graph that are outside. Now, of course, the difference is less or equal than the total measure of this region here. Not only the graph, the total measure of this region here. And since Mn projects to mu, that measure is exactly the measure of mu, the mu measure of the complement of K. Is 1 minus epsilon. Okay, so I think I should say bigger or equal than, because I'm excluding the whole region. But anyway, this is true for every n. Okay? The fact that all these measures project to mu means that I can estimate the weights, the masses of those measures, the regions, just by projecting here. Everything in the yellow region, which doesn't project to K, has total measure less than epsilon. Okay? The conclusion is that, just look at this. The conclusion is that M0 of this part of the graph is bigger or equal than 1 minus epsilon. Okay. And so if I making epsilon go to 0, of course, when I make epsilon go to 0, I have to choose compact sets that are bigger and bigger. I conclude that M0 of xv with v in vxj is equal to 1, which is precisely what I wanted to prove. Okay? This fact here was, it's not an obvious statement, because we have this measurable subbundle, and how is this measurable subbundle going to behave under limits? But in a sense, what is being used here is that if it is measurable, then it is continuous. And if it is continuous, the graph is a closed subset. And measures cannot escape from closed subsets. So this proves that the set is closed. And now invariance is obvious. You just take the image of a measure, then you calculate on the graph. And by definition, this is M0 of the preimage of the graph. But our subbundle is oscillated subbundles are invariant. So the preimage is, and if you have an invariant subbundle, the graph is also invariant. So this is M0 of xv v dxj, and this is equal to 1 by assumption. Okay? So there's not really much to say. This set is invariant under the cocycle because the set involved in the definition is invariant under the cocycle. Okay. So this proves the lemma. And so we also, at this point, we know so now we know that it's done, that there exists some PF invariant measure, probability measure M, such that the measure of the graph is 1. Okay? So the only thing that is missing is this. Now, the integral of phi dm is equal by Birkhoff is equal to the integral of phi twiddle dm, where phi twiddle is the Birkhoff average. Phi twiddle of xv is limit 1 over n sum is equal to this limit. This is just Birkhoff. And the rest of the proof is something that we already did. Phi is written there. You just write it down. You replace it here. And so you get log of A of fj of x v divided I already did this calculation. It's it's just the definition of phi and the definition of the projective cocycle. And how now we have a telescopic sum here. So this is equal to the limit 1 over n of log anx v divided by v, because all these cancellations, these terms disappear. You have j plus 1 here, you have j here. And you have logarithms that are subtracting. So the limit is equal to, this expression, this sum, is just, you can simplify to this one. The denominator is irrelevant because log norm v divided by n goes to 0. So you will only have to look at the numerator. And the numerator is the Lyapunov exponent of v. And since we are taking, we only have to consider points v in this set because the set has full measure. This is equal to lambda j. Right. Because for x v such that for v in vxj. Questions? And, you have to have questions. This is not properly done yet. So what are the questions? What are the questions? Complaints? I don't know. I haven't said that it is ergodic. I didn't say it. But I used it. Huh? No, wait. I don't know. I mean, I'm sure it has to be. It can be chosen ergodic, but I don't know how to prove it is ergodic. I thought I didn't need it. I thought I could get away with it. Yeah. This depends on X. There's another problem, and I don't have a solution to either of the two. There's another problem. Here I said that the limit is lambda j because the vector is in vj. That's not exactly what we have, right? We have the flag. and we have that the limit 1 over n log an of x v is lambda j of x for v in the difference So there are two difficulties, and actually it's not written properly there. It's not correct. So how are we going to solve them? I don't know. I will have to think. I don't think we need ergodicity to begin with. Ergodicity is not a, I mean, the right statement is with ergodicity there, but if I don't write it, I don't have to prove it. Okay? So, and I don't think we actually use it. This is true always. All this is correct. And the limit is lambda j, because I am assuming here, I didn't write it, but I'm assuming that f mu is ergodic. This I wrote last time and I forgot this time. Okay, so the Lyapunov exponents are numbers. The ergodicity that I use is that one. Okay, so then this is a number. And that's all I need. If phi twiddle is equal to lambda j almost everywhere, then this is equal to lambda j. That's the end of the argument. Yeah, I do need to. That's another problem. For that I don't know what. I don't know. I have to think. I should take f dj plus 1 out. That's another problem. But the ergodicity is not used at all. That m is ergodic is not used. But this you're right. I would have to argue that I am. Okay, so this is not completely proven. I will have to think. It's not well written either. It's kind of funny because at the time I thought about this. This is not correct. Okay, I'll think about that and then hopefully I will fix the text. So, okay, so I will probably come back to this theorem, but for the time being, let us stop here. I have to fix this. Now, I want to move on to proving something that we are going to use more directly, which is the theorem of Furstenberg's formula. That I'm going to state, and then I have to explain some of the objects that appear in the statement. It says that the largest Lyapunov, the context is always the same, so I go directly to the conclusion. it says that the largest Lyapunov exponent is the maximum of, and it is related to this theorem, although not, the relation is not entirely trivial, is the maximum of the integrals of phi, and I'm going to write more things. So this theorem says that every Lyapunov exponent is realized as the integral of phi with respect to some measure, some invariant measure. And of course, then the largest Lyapunov exponent is the largest value of these integrals. That's easy. But I'm going to say something a lot more subtle. Is equal to the maximum of the integrals, not over all measures, but over product measures, such that eta is a measure on, I'm going to write the word, a stationary measure on projective space. Well, this is not quite Furstenberg's formula. Let me call it theorem of Furstenberg. So this theorem seems to be a direct consequence of this, because I'm taking the maximum of these integrals, and I'm saying that it is equal to the largest Lyapunov exponent. And it would be an immediate consequence if I took the maximum over all invariant measures. But I don't. I take the maximum over measures of this type. And I'm going to explain that. Okay? So the main point is that here I have product measures. Okay, so for that I have to start by explaining what a stationary measure is. So here, I said that the setting is always the same, but it's not true. See, here I'm considering a linear cocycle F and the corresponding projective cocycle M. Where M is a shift space, is equal, is a space of sequences on some set X, and then F from M to M is the shift mapped. So this is the Lyapunov exponent associated to mu. And then mu is a Bernoulli measure. So you have this general statement that only asks for ergodicity of the system, and you have a much more restrictive setting here, where you assume that your transformation is a Bernoulli shift. And an A, so another assumption is that A, which in principle is defined from M to GLD, M is a space of sequences. I'm going to ask, or I'm going to write that over there, and A is locally constant. This is an expression. When you have a function defined on a shift space, on a space of sequences, you say that it is locally constant if it only depends on the first coordinate. On the zeroth coordinate. Okay? So this is the situation. And then we say that eta, a measure, a probability measure, eta on projective space is stationary if eta of d is equal to the integral of eta of ax minus 1 of d mu x for any measurable d in projective space. So what this means, let me first simplify the definition. The definition is actually very natural. Let me first simplify it. A of x is this. It's a sequence like this. A of x only depends on the zeroth coordinates. Okay. When I say that mu is a Bernoulli measure, I mean that mu is some measure is a product, a countable product of some measure, countable power, or nu to the z. So A of x only depends only on the first coordinate, like 0. And I can use this here. So the definition is the same as saying that eta of d is the integral of eta. Since it only depends on the first coordinate, I'm going to abuse language a little bit and write only the first coordinate here. Okay. And then I have to integrate with respect to the first coordinate. That's since I only have one coordinate, I only have to use one factor here. The integral. Is this understandable? Because if this is the beginning of something, if this is not clear, then the rest will be completely impossible to understand. So let me give an example here. Example. Suppose that X is a finite set. Finite set. And nu is a probability in X. This nu here is a probability in X So it is given by a probability in a finite set is just given by the weights of the points. Is given by this, by the weights of the points. A, so M is the space of sequences, say x to the n or x to the z. A is a function from M to matrices. But since I'm assuming that it only depends on the first coordinate, I can think of A as being a function from X to matrices. Right? Just use the first coordinate, which is an element of X. And a function on a finite set is given by the images of the points, A of 1, A of n. Okay. So I'm defining what a stationary measure is. That's a measure in projective space. Here is projective space. Okay, it's a measure here. So what is the property of a stationary measure? What does the definition say? Well, the definition says that eta of d is the integral of these numbers with respect to nu. Nu is a probability on a finite set. So instead of integrating, I just sum. The definition is that eta of d is equal to eta of ai minus 1 of d. And then I'm integrating, which means that I have to multiply by the weight of I from 1 to m. This is in the case where x is a finite set. This is the same thing as this one. Or that one. Okay, so what does this mean? It means that I take any domain D here. I look at the pre-images, A1 minus 1 of D through A n minus 1 of D. Look at all those pre-images. I measure them. I measure the pre-images. Then I take the average of those measures. The average with respect to the weights, nu1 through nu(n). And I want that the average of the measures of these pre-images is equal to the measure of the set. Okay? So when you move forward, the measure remains the same. The measure here is the average of the measures on the pre-images with the suitable weights. That's what stationary means. Not really. I cannot prove that there's any sort of finiteness. What I think this is saying is that among all the invariant measures, those that are products are more likely to maximize the exponent. Not all of them necessarily do that, but they are more likely to maximize the exponent. That's something that let me maybe state something here, and that should help a little bit to understand this. So lemma, eta is stationary if and only if the product is PF invariant. Okay, so the projective cocycle has many invariant measures. Some have the special feature that they are, all of them has plenty of invariant measures projecting to mu. All these measures are in project down to mu. But among them, some are product measures. And when they are product measures of mu times something, this something is stationary. That's what it means to be a stationary measure. Okay, so you could take this as the definition of stationary. Okay, and those measures are, according to this statement, more likely to give you the largest Lyapunov exponent. Now, maybe for the sake of giving you the full picture, maybe at this point I can state another theorem. It's called Furstenberg's formula. It says, there's an assumption, assume that the cocycle is completely irreducible. I'm going to define that. That's an assumption. Completely irreducible. Then the largest Lyapunov exponent is equal to the integral of phi d mu times eta for any stationary measure eta. So this other theorem says that under some assumption that I still have to define, in fact, all of these product measures give the same weight to the integral of phi. So all of them realize the largest Lyapunov exponent. Okay. Completely irreducible means there does not exist a finite family L of vector subspaces of Rd such that Ax of L is equal to L for mu almost every x. That does not exist. So you have all these matrices, A of x, and the definition means that it is impossible to find a finite set of subspaces that are invariant under all of these matrices. For example, in 2 dimensions, there does not exist any finite family of lines that are eigenspaces of AX for almost every X. Okay? Just to see if you are, I'm giving you too much information at the same time, but I think it's necessary to understand how these results connect to each other. What is your feeling? Are most co-cycles completely irreducible or completely reducible? What is easier to get? Reducible or irreducible? Irreducible. Irreducible is much easier, because to be reducible, there has to be some number of subspaces that are fixed by A of X, by the matrix A of X, for almost all X. If I give you two matrices, it will already be difficult. In general, they will not have any common invariant subspace. Okay? So most co-cycles are irreducible. And when they are irreducible, Furstenberg's formula says that all product measures, all measures of the form mu times stationary, realize the largest Lyapunov exponent. To the twisting condition. Yeah, in the text I discussed the relations between the two. They are not quite the same, I think. But I thought about that, and whatever I could discover, I wrote down as exercises and so on. But this is very close to. There's a notion of irreducibility, where you say there does not exist one vector subspace that is fixed by all the matrices. If you make the condition slightly more flexible with the finite family instead of only one, then you speak of complete irreducibility.
This property isn't connected with the dimension of the space of stationary measures.
I don't think so. I don't think so. I thought that sort of questions a little bit, but I think even in this situation, there could be a lot of stationary measures. It's just that they all give the same weight to phi. I thought I could prove like there exists only one or so, but it's not. I don't think that's true. I don't have a proof, but I don't think that's true. Here in this definition, yes, the subspaces don't need to be invariant, but this family is invariant. Yeah. Example of a not completely reducible co-cycle. You take the Bernoulli case with x equals 1, 2. A of 1 is 2, 0, 0, 1 half, and A of 2 is 0, minus 1, 1, 0. Okay? So the first matrix is hyperbolic. This is the expanding eigenspace. This is contracting eigenspace. That's A1. And then A2 is the rotation by 90 degrees. Okay? This co-cycle is irreducible. But not completely irreducible. Why is it not completely reducible? Because I can find a finite family of subspaces namely the x-axis and the y-axis, and this family is invariant. Neither of the two is invariant under A2, but the family is invariant. Okay? But it is irreducible. That's easy to see. There is no line invariant under both matrices. In fact, there is no line invariant under this matrix, even without counting the other one. Right? So this is irreducible, not completely irreducible. So the theorem doesn't apply. Furstenberg's formula does not apply in this case. And in this example, that is related to having more than one stationary measure. I'm going to exhibit two stationary measures. Remember, stationary measures are measures, they live in projective space. And there are at least two stationary measures. Eta 1, which is well, actually, I can only find one stationary measure. Where delta x is direct mass on the x-axis, and delta y is the direct mass on the y-axis. Can you find any other stationary measure? So exercise. In this example, there is only one stationary measure, namely this one. I think this is true. I'm not entirely sure, but I think this is true. So this means that in this example, although it's not completely reducible, still the Furstenberg's formula is true. Okay, let me, I'm going to prove the lemma. And then I will state a few properties of stationary measures that I'm not going to prove, but that are useful. So I've been moving a little bit from chapters 5 and 6 back and forth. Right now I am in chapter 5. This is in chapter 5. Okay, so I'm going to do the following thing. I'm not going to prove the theorem in general, the lemma. I'm going to prove it in the case x is finite. You have the complete proof in the book, but I'm going to prove in this case. And then mu m is x to the power n. And then you have a measure, a probability in x. And then you have the Bernoulli measure corresponding to it. Okay? I mean, if I write the proof in general, you will forget it in 5 minutes. And I think if I do the simplest possible case, you will never forget it. So we have the projective co-cycle acting here. Remember that A, locally, I'm assuming locally constant. Okay. So I'm going to look at the measure mu times eta. And I want to check that this measure is PF invariant if and only if eta is stationary. So I have to look at the image of this measure, calculate it on some set, and then compare to the measure of that set for mu times eta, without the push forward. Which set should I take? This is a measure in product space. I don't need to take all measurable sets. It's sufficient to take any family of measurable sets that generates the sigma algebra here. So I'm going to take a cylinder I think I already defined this here. This is the set of sequences x in M such that x0 equals I0, x1 equals I1, etc. xn equals in. So these cylinders generate the measurable structure on M, and then I might multiply by something, D. D is any measurable subset of projective space. Okay? So I'm going to look what is the preimage of this, what is the measure of this. Now, by definition, this is mu times eta calculated on the preimage Pf minus 1 of 0 in times d. This is what iterating forward means. The co-cycle, what it does is that it takes xv goes to f of x ax of v. Okay, so now we have to think what is the, how do you calculate the preimage? Well, the preimage for the shift here in this coordinate is easy. preimage of the cylinder is you just have to translate the cylinder to the right. So is the union over all possible values of x of 0, I, I1, In. This is taking the preimage at the level of the shift. And then you also have to take the preimage in the second coordinate, and that's easy. That's a of x minus 1 of d. It's not very well written because what is x? Well, fortunately, I'm assuming that a is locally constant, so a depends only on the first coordinate, and the first coordinate here is I. Okay. That's one of the places where I use the fact that A is locally constant. Okay. So in this finite setting, when you take the preimage, you have to choose which coordinate you're going to insert here because you're shifting to the right, and then that determines also which matrix you take in the preimage. Okay, and now I'm going to calculate this. This is a disjoint union, so the measure is the sum of the measures of mu of 0, I, I1, In times eta of AI minus 1 of D. Okay, I'm calculating this expression here to see when and how it is equal to mu of eta of this set. Now, this is the right place to use the fact that the measure mu is Bernoulli. This measure is equal to pi times, look at this, the measure of 0, I1, In. Because the measure being Bernoulli, this is equal to pi, pi1 through pin. And this is equal to pi1, pin. Okay? Here I use the fact that the measure is given by products. So this factor does not depend on I, so I may take it out. And then what is inside is the sum pi eta ai minus 1 of d. And you want this to be equal to, so Pf star mu times eta of 0, I1, In times d is equal to mu times eta of the same thing. If and only if, let us compare. We have this, which is fine, which is here. And then we need that eta of d is equal to the sum this here, this is just mu of the cylinder times eta of d. So for the two expressions to be equal, this factor has to be equal to this factor. And that's what I'm writing here. Okay. In other words, this is true for all sets of this form, if and only if this is true for all sets of this form. So P F star of mu cross eta equals mu cross eta, if and only if eta is stationary. Okay. And that's the proof of the lemma. Okay, I think I'm going just to state some properties of stationary measures, and then we stop for today. Here are some properties. Proposition. If f is continuous, yeah, if if M is compact, the reason I'm hesitating is that the statements in the book are much more general than what I'm doing right now. Okay, so in this setting, the proposition says there always exists the set of stationary measures is non-empty. So in this context that we are in, stationary measures always exist. And closed. And this is an interesting property. If you have a sequence of stationary measures converging in weak star topology to some measure, the limit is also a stationary measure. Another proposition. The following are equivalent. So we say that a function is stationary It's the definition for functions. If phi of y is equal to the integral of phi of v is equal to the integral of phi ax minus 1 of v mu of x. The definition formally analogous to the definition of stationary measure, but this is definition for functions. And then the proposition says that the following two properties are equivalent. Every stationary measure is constant. So I need a slight generalization of this. We say that phi is eta stationary if this is true for eta almost every point in projective space. Okay. Every stationary measure, every stationary function is constant eta almost everywhere. This is one condition. The other condition is that, okay, I need the notion of stationary set. We say that a set D, PRD, is eta stationary if the characteristic function is eta stationary. In other words, if the characteristic function is eta stationary. So another condition here is that every eta stationary set D has measure 0 or measure 1. So for you, with some familiarity with ergodic theory, this should be a transparent statement. The proof maybe not so transparent, but the statement is transparent. It is saying that given a stationary measure, it's the same thing to say that every stationary set has measure 0 or 1, or that every stationary measure function is constant. Then, if either of the two conditions is satisfied, then we say that eta is an ergodic stationary measure. And then we have a theorem called the ergodic decomposition. Ergodic decomposition theorem. We have a lemma. Before that, a lemma similar to this one, saying that it's a stationary measure eta is ergodic if and only if the product measure is ergodic for PF. So this statement says that stationary is the same thing as PF invariant, and then there's a counterpart at the level of ergodic measure saying that stationary measure is ergodic if and only if this product measure is also ergodic. And the ergodic decomposition theorem says that every stationary measure eta may be written as a linear combination. Eta is the integral. What is the notation? Yeah. D. Oh. It is the integral eta d. C of d. D hat C, where eta is a measure concentrated on, it's a probability measure that gives full weight to the set of ergodic stationary measures. Okay, it's just one way of writing. It's easier to understand than to write down. Just one way of writing that any stationary measure may be written as a linear combination of ergodic stationary measures. I will come back to this on Thursday. I think for the purpose of this presentation, I'm going to focus a lot more on the two-dimensional case, because that allows me to give examples, not just come up with notions and statements. It allows me to, so I will probably focus more on the two-dimensional case, but that's, we'll come back to this on Thursday. Questions?